You're probably focused on the Cybercab rollout, which means you're missing the 5.2 million square foot shadow project right next door. Welcome to Giga Texas North. The workforce here doesn't commute, they arrive in shipping crates, boot up, and get to work. We're looking at a facility engineered specifically to remove human labor from the equation entirely. But think about the logistics for a second. How do you physically construct a campus meant to pump out 10 million humanoid robots a year? You don't use legacy, industrial logic. You deploy a lightless, hyper-dense environment where autonomous swarms mathematically choreograph their own construction. You power it with a bespoke silicon compute forge that closes the loop between frontier AI training and real-time physical action. And you completely abandon the traditional two-dimensional factory floor plan, shifting to vertical microcells perfectly synchronized inside a digital twin. This is far beyond a standard factory expansion. It's the foundation of the first true Terafab. So, what actually happens when power materials and compute are forced into a space optimized only for machines? How do you sequence an automated build-out when human presence is treated as a critical exception? But to understand the Terafab, you have to look past the architecture and into the kinetic soul of the factory itself. It begins at the substrate level, where the line between software and physical matter completely disappears. So, how does an auto construction loop actually function in the dirt? Built by robots isn't a marketing slogan here, it's a recursive mathematical cycle of plan, simulate, deploy, and self-improve. At the ground level, Optimus is the physical worker, highly dexterous, perfectly repeatable, and safety-rated for hyper-dense environments. First-gen units pulled from the Fremont pilot line are already deployed here, managing site logistics and handling structural assemblies. But Optimus is just the hands. The autonomous mobile robots, or AMRs, form the circulatory system of the entire site. They route pallets, spare parts, and tooling with sub-centimeter accuracy, running 24/7 without weather delays. Even the foundation work is algorithmically scheduled, with drilling rigs and material drops sequenced to mathematically eliminate idle time. A central planner computes every single lift window, optimal path, and collision-free handoff across a massive mixed fleet. Concrete pours, curing times, and laser inspections operate in a closed loop, feeding real-time sensor data back to the master schedule. And when ground congestion spikes during critical operations, automated aerial resupply steps in to completely bypass the bottlenecks. This ruthless efficiency reaches its peak inside the true human zero zones. Step inside, and you'll find no lighting, no HVAC, and no safety walkways. Every cubic inch of space is optimized for hardware. Thermal budgets and airflow are directed exclusively at cooling machines, making human access exception only and heavily audited. Without shift changes or union breaks, nighttime simply means a lower ambient thermal load on the facility. If a machine fails, the robots self-diagnose, schedule their own maintenance, and physically stage themselves for repair. Standardized factory modules even allow the robotic workforce to tear down and reconfigure entire production cells without human rigging crews. Every physical handoff is planned in a digital twin first, then executed in the real world with time-locked precision. As a result, the efficiency KPIs aren't just improving, these recursive hardware upgrades are compounding weekly. But choreographing thousands of autonomous machines in a massive, dark factory requires an incomprehensible amount of real-time processing. To control a physical loop this complex, you need an intelligence engine unlike anything ever built, and it's sitting right next door. That engine is the Terafab, the first facility designed to close the loop between frontier AI training and custom silicon production. This isn't a traditional assembly line, it is a high-density compute forge where Tesla, SpaceX, and xAI interests converge. To run a human zero factory, you can't rely on off-the-shelf hardware that wasn't built for the specific latency of humanoid kinetics. It starts with the Cortex clusters, massive supercomputers that ingest multimodal data to train the next generation of neural networks. These models are then distilled into optimized binaries, specifically compiled for the proprietary AI5 Silicon produced right here. The AI5 chip is the centerpiece, a bespoke inference workhorse designed to handle the frame-to-action pipeline of Optimus V4. We are looking at a tiled NPU fabric with massive on-die SRAM, optimized for ultra-low latency sensor fusion. Compared to previous iterations, this silicon offers a 50x increase in processing power, enabling near-instantaneous physical responses. Every chip is built with package-level cooling to ensure deterministic performance even under the most extreme thermal loads. The compiler schedules memory with cycle-accurate precision, removing the jitter common in general-purpose AI. Advanced packaging techniques allow for extreme memory proximity, bypassing the traditional bottlenecks of data movement. Before a chip ever reaches a robot, it undergoes a rigorous soak test to weed out any potential hardware failures at the wafer level. Once validated, the compute module slides into the Optimus chassis like a server blade, shock-rated and environmentally sealed. Software updates don't just fix bugs, they recalibrate the hardware's policy based on the latest fleet-wide edge cases. This creates a relentless cycle where field data flows back to the clusters, and new silicon architectures are born from the results. This synchronization of capital, launch logistics, and AI research is what makes the 10 million unit annual target even possible. Every wafer start is mathematically aligned with upcoming model releases, ensuring the hardware is never the bottleneck. But even with the world's most powerful brain, you still have to solve the three-dimensional problem of mass production. If silicon is the brain, the factory layout is the nervous system, and Giga Texas North is abandoning the concept of the floor plan entirely. When you abandon the 2D floor plan, robot production instantly becomes a massive three-dimensional optimization problem. Kilometer-long conveyors are dead. They've been completely replaced by high-density, verticalized manufacturing cells. Material lifts feed components directly to stationary assembly nodes, drastically compressing the physical footprint and takt time. Inside these microcells, vision and force sensors run continuous inline metrology, executing actuations with zero transit delay. Even the kitting geometry is calculated strictly by pick frequency, enforcing pure mathematical efficiency over legacy traditions. As production scales, cells self-report their metrics, allowing the central planner to dynamically shift loads before physical bottlenecks form. But you don't test a workflow this complex on real hardware, you run the entire campus inside the digital Optimus twin first. This isn't just a 3D model, it's a hyper-accurate simulation with real-world physics, control loops, and material constraints fully baked in. Thermal spikes and traffic collisions are solved entirely in simulation, then pushed to the production floor as verified updates. Trajectory planners map out every autonomous movement in silicon, guaranteeing safe separation while maximizing robotic arm overlap. It even runs energy-aware scheduling, flattening power spikes to preserve critical thermal headroom inside the human zero zones. By the time physical assembly actually begins, the outcome is already mathematically guaranteed, setting the stage for unprecedented global scale. What we're witnessing at Giga Texas North isn't just an incremental step in manufacturing, it's a total decoupling from legacy industrial logic. By integrating custom silicon, recursive auto-construction, and hyper-accurate digital twins, the human zero threshold has moved from theory to reality. The Terafab represents the first true physical manifestation of an AI-first economy, where the speed of production is limited only by compute. If Tesla successfully scales this to 10 million units annually, the global labor market doesn't just change, it resets. But a transition this massive brings up a critical engineering question that we have to address. Can a fully autonomous loop truly handle the edge cases of physical reality, or will a human hand always be the final safety net? I want to hear your thoughts. Drop a comment below on whether you think the Terafab can truly scale without a human on the floor. If you're a techno-optimist who values data over hype, make sure to subscribe and hit the notification bell. Thanks for watching, and we'll see you in the next deep dive into the accelerated future.